Okay, good afternoon, everyone. Good evening. Yeah, so let's get started.
Okay.
Good evening. So, yeah, so we were discussing this transient one-dimensional heat conduction equation. Transient one-dimensional heat conduction equation. Essentially, we wrote this as partial u by partial t equals alpha dou square u by dou x square, right? That's what we have written. And we said that essentially this can be discretized using different methods, right? Where alpha is the thermal diffusivity, t is the time, x is the spatial coordinate, and u is the temperature that we want to solve in a one-dimensional domain, right? So we said essentially if you take a domain like this is a bar or a beam, something like that, where you need both the boundary conditions, boundary condition 1 and boundary condition 2, and the initial condition. With that, you'll be able to solve for this. However, you need to discretize it with different methods. We said there are several methods you can use. We looked at only 3 of them, which is called the Euler's explicit method, or the forward time-centered space, which basically gave us uin plus 1 minus uin divided by delta t equals alpha times ui plus 1 minus 2ui plus ui minus 1 divided by delta x square, where on the right hand side everything is evaluated at time level m. Then we basically get an Euler explicit method, in which case you can calculate uin plus 1 at the ith grid point simply by substituting for the known values of uin, ui plus 1n, and ui minus 1n, and so on, right? So you can simply substitute for these values and then calculate. Okay. Now we looked at another method that is known as the implicit, the Euler's implicit method. This is the or explicit Euler or implicit Euler. It can be even said like that. Okay. So this is the implicit Euler method, which is also known as backward time-centered space. So the discretization with respect to the space is going to be the same. It is still the second-order central difference scheme, whereas with respect to time, we are going to evaluate everything on the right-hand side at the unknown time level rather than at the known time level, right? So essentially, that means it's going to be uin plus 1 minus uin divided by delta t equals alpha times ui plus 1 n plus 1 minus uin plus minus 2 ui plus ui minus 1, where everything is evaluated n plus 1 divided by delta x square. Okay, that's what we have written. Of course, as the name backward time suggests, this can be written with n plus 1 and n in this form, or you can even replace n plus 1 to match with n, and then n with n minus 1. You will also see this kind of treatment in certain textbooks, where you will write this as ui n minus ui n minus 1 by delta t equals, on the right hand side you will have ui plus 1n minus 2 ui n plus ui minus 1 divided by delta x square. We realize that both these formulations are the same, in a sense that we are moving from n to n plus 1 in this formulation, whereas we are moving from n minus 1 to n in this formulation. Okay, essentially what is on the right hand side is an unknown time level, right? It happens to be n in the case of the second one, and it happens to be n plus 1 in the case of the upper one. Okay, so either you can write it in both ways. Now we also looked at essentially another method that is known as the Crank-Nicholson method. Which we said is going to evaluate all the values at n plus 1 time level instead of at n or n plus 1, n plus half time level instead of at n and n plus 1, like in the explicit Euler or implicit Euler. Okay, so in which case we're going to write this as partial u by partial t at n plus half equals alpha dou square u by dou x square at n plus half. So the left one is going to be still the same as before. It's going to be now un plus 1 minus uin divided by delta t. Now this is a centered scheme about n plus half, and on the right hand side we're going to write this n plus half value of alpha dou square u by dou x square as alpha times dou square u by dou x square at level n plus dou square u by dou x square at level n plus 1. Right? That's what we're going to write. That means this is going to give us alpha times ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square, evaluate n plus 1, n plus 1, n plus 1 plus ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square obtained at n, 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 n. Okay, so that is your discretization for Crank-Nicholson scheme. Okay, fine. So then once we have this thing, we're going to, we said, although it is easy and straightforward to comment on the truncation error, for the above discretization schemes. We're going to develop a formal method for the evaluation of truncation error. Okay, so that is what we're going to see next. So we're going to essentially look at what is the truncation error for these schemes, that is the Euler explicit scheme, and maybe we look at the truncation error for Euler for Crank-Nicholson scheme. Maybe you can calculate on a similar lines what is the truncation error for the Euler implicit Euler scheme later. Okay, fine. Any questions so far? I think I just give a quick recap of what we learned towards the end of the lecture yesterday. Before I get started with the calculation of truncation. Any questions or comments that you have? Okay. Fine. So let's look at the truncation error. So we already said what is truncation error. Essentially, you have this differential equation. Basically, you have a on one hand, you have the partial differential equation, which in this case is basically dou u dou t equals alpha dou square u by dou x square. That means I can write this as a function of dou u dou t and then dou square u by dou x square equals 0. So this is my sum equation that is involving first time derivative and second spatial derivative. Okay, and similarly, we have the final difference equation, which is essentially some f that involved u at I, u at I plus 1, u at I minus 1, and so on, right? Essentially, this involved n values or ui at n plus 1, and so on. That means we have a final difference equation equal to 0, right? We have basically one such equation, and in fact, we have n such equations, which are together form the set of linear algebraic equations. So that is the final difference equation. This is the partial differential equation. Now that means our little u, which is the exact analytical solution, is going to satisfy. Okay, my u doesn't look like u. So u, the exact analytical solution, is going to satisfy the partial differential equation. That means f of u equals 0. Similarly, the f capital U is going to satisfy, if I were to write fu is going to satisfy ui comma n etc. is going to satisfy the final difference equation, right? The algebraic equation. But then the exact analytical solution, that is little u, is not going to satisfy the final difference equation, right? This is not going to be 0. And then we said the amount by which the exact analytical solution fails to satisfy the final difference equation, that is known as the truncation error. That means this is not equal to 0, and what is that value that it is not equal to 0 is the truncation error for this problem, right? F of little u is the truncation error. Okay, so let us see how to calculate this truncation error for the one-dimensional transient heat conduction equation, and then we'll also comment about two things. One is calculation of truncation error. Second one is the scheme consistent or not? Okay, that means once we're going to obtain the an expression for the truncation error, we're going to see as we make your delta x tend to 0 and then as delta t tends to 0 is the truncation error tends to 0, right? And we can say that the particular scheme we are using is a consistent scheme. Okay, so that's what we're going to do. Okay, fine. Then let us start with this explicit Euler method. Okay, so explicit Euler method, if I'm going to write the final difference equation in terms of capital Ui and other quantities, we can write this as so the final difference equation, which is satisfied by the Ui, capital Ui's, that is going to be written as Uin plus 1 minus Uin divided by delta t equals alpha times Ui plus 1 minus 2 Ui plus Ui minus 1 divided by delta x square at the time level n, and n. Okay, so that is my final difference equation. Now we know that we want to write this final difference equation. So to calculate the truncation error, I need to write this final difference equation, whatever I have here, which is and substitute for the exact analytical solution in there. That means I want to rewrite this FDE with little u there instead of capital U, right? So this we know that essentially if I bring this equation to, if I write minus, this is equal to 0. But then the moment I put in FDE with little u, then this is not equal to 0, right? This is not equal to 0. This is the truncation error, right? Whatever the amount by which it is not equal to 0 is the truncation error. That means I'm rewriting this to calculate truncation error as little u I n plus 1 minus I n divided by delta t minus alpha times we'll have ui plus 1 n minus 2 ui plus ui minus 1 n divided by delta x square, right? That is my truncation error. Okay. Okay, now we know that essentially this little u is the exact analytical solution. So as a result, it will have smooth and continuous derivatives with respect to space and time, right? With respect to space and time, it's going to have smooth and continuous derivatives. So then we can make use of expanding again these things about using Taylor series about a particular point. That means now I want to again still recall Taylor series. So I want to convert this equation such that I can evaluate what is the truncation error that is involved. That means I'm going to invoke Taylor series for each of these terms. That means I want to invoke Taylor series and then write ui n plus 1 in terms of ui n. Similarly, I want to invoke Taylor series for ui plus 1 n and ui minus 1 n, and then write them in terms of ui n, so that the entire equation will be in terms of ui n and its derivative at ith point at nth time level. Okay, that's what I want to write this equation as. So for that, I'm going to use Taylor series expansion and then write this as ui n plus 1. Now I'm expanding about ui n, and then we realize that we are now expanding not about space but about time. So as a result, let us take delta t is the time step or between n and n plus 1, and similarly delta x is the spatial difference. Okay, so as a result, ui n plus 1 equals ui n and then plus delta t. Okay, then I can write this as we'll have dou u by dou t at I and n. Okay, that's what we have. And then we have plus delta t square by 2 dou square u by dou t square at I and n, and so on. That's what we'll have. Okay, so but then I want to slightly rewrite this thing so that the convention will be easy for us. So ui n plus 1 uin plus delta t. I'm going to write dou u by dou t as u sub t. Okay, the moment I write u sub t, that is going to be partial u upon partial t. Okay, I'm writing a small notation here so that it is easy. Delta t square by 2 u sub tt. That is going to be same as dou square u by dou t square plus delta t cube by 6 u sub ttt and so on. Okay, so that is the convention I'm following. That means I can now write an expression for uin plus 1 minus uin by delta t from here by bringing uin to the left hand side and then dividing throughout with delta t as uin plus 1 minus ui divided by delta t will basically give me u little t, okay, which is of course calculated at I comma n, which I have not been writing all the time, plus delta t square by 2 when divided by delta t is going to make it delta t by 2 u sub tt again at ith level, at ith location n, plus delta t square by 6 u triple t at I comma n and so on. Okay, so you should see the process. Okay, so don't worry about that there are too many terms, all those things. You will, once you understand the process, you should be able to do it with any other equation that is given to you using a similar process. Okay, so we started off with writing the final difference equation in terms of the capital U, which is the numerical solution for the set of algebraic equations. Then we have replaced the capital U with small u. Small u is the exact analytical solution. We have put that into the final difference equation. Okay, that's what we are doing. Okay, then we have obtained some series for, let us say, the first term, that is uin plus 1 minus uin. So for this first term, we obtained some series. Okay, let us say this is there. So I have this continuous series, which is now, if you see everything on the right hand side, is in terms of either the function value or its derivatives at ut, utt, and so on at ith grid point at nth time level. Okay, so that is how it is organized. Okay, similarly, let's try to now expand this uin plus 1, ui minus I minus 1. But now all of these are at the nth time level, right? Because this is an explicit scheme. So as a result, everything is at nth time level. So I'm going to write this as ui plus 1 at nth time level as ui at nth time level plus delta x. Then you have, typically you'll have dou u by dou x at I comma I and n. So I'm going to use this shorthand notation. Instead of dou u dou x, I'm going to write u sub x. Okay, this is exactly same notation we have followed. If the derivative is with respect to time, we're going to write it as dou u dou t. If the derivative is with respect to space, we're going to write it as ux, okay, instead of ut. And then plus you will have delta x squared by 2 factorial u sub xx plus delta x cubed by 6 u x double x and so on. So essentially now what we have is, and of course again these are all at I comma n. Okay, that's what we have. Similarly, I can also write ui minus 1n. That is going to give me uin plus, sorry, because this is minus, we're going to get the odd terms as minus and the even terms as plus delta x squared by 2 u sub double x cubed by 6 u x, and then plus, sorry, this will be a minus here again, and this will be a plus and so on. Okay, that's what we have. Okay, now in order to obtain this second term that we have, that is ui plus 1 minus 2 ui plus ui minus 1, I'm going to simply add the two equations we have. I'm going to simply add these two equations, because if I add them, I know that I'm going to get ui plus 1 plus ui minus 1, and then on the right hand side we'll get 2 ui, which one goes to the left hand side will become minus 2 uin. So that means this is going to be, if I add these two equations, you get ui plus 1n plus ui minus 1n minus 2 uin, right? Once I add these two values, I have taken to the left hand side. Okay, then when you add delta plus delta x and minus delta x is going to become 0, and delta x squared by 2 uxx, this is basically 2 halves becomes 1. So this is delta x squared uxx. Again, this gets cancelled, but then that reminds me I should get one more term, delta x power 4 by 4 factorial u 4x. Okay, so this is delta x power 4 by 24, 4x and so on. Okay, plus, minus and so on. Okay, this is delta x squared u double x, uxx. That's what we have. And then we'll get plus delta x power 4 divided by 24 will become 12 because we got two of them. Okay, times u fourth derivative of x, okay, and so on. That is what we would get. Okay, so what is this? This is basically, if I were to write ui plus 1 minus 2ui plus ui minus 1, all at the nth time level divided by delta x square, then this is going to be, this is uxx plus this is going to be delta x square by 12, right? We are dividing with delta x square everywhere, times u 4x values, and then this thing. Okay, so let us say this is equation 2. So we have equation 1 and equation 2. Now we can substitute for these two in the expression for truncation error. Okay, so what we have done is we wrote the truncation error in terms of the little u quantities. Then we expanded n plus 1 quantities about n, I plus 1 quantities about I and n, and then we obtained an expressions for these two quantities, that is ui n plus 1 minus ui by delta t, and then the second quantity, that is ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square. So I'm going to go back and substitute for this. Remember, there is also an alpha that is multiplying the second term here. Okay, so my truncation error is now going to be, truncation error is equal to, from the first equation, what I have is, from the first equation, I'm going to substitute. I have ut plus delta t by 2 utt. So this is ut I comma n plus u delta t by 2 utt at I comma n. So I'm not writing this I comma n. We realize that it is basically there. Okay, and then delta t square by 6 u triple t is what we have, and then we have then minus alpha times this quantity, that is nothing but is replaced with the what is there on the right hand. This is going to be uxx, again this is at I comma n, plus delta x square by 12 u xx, and then order x to the power 4. Okay, that's what we'll get the next term. Okay, so this is the truncation error, but then I can now bring this term and this term together. That is going to be ut minus alpha times uxx at the time level n at the grid point I, plus we have delta t by 2 utt, and we have minus alpha times delta x square by 12 uxxx plus order delta t square plus order delta x power 4. Okay, that's what we have. Okay, so what is this value? This value is nothing but dou u dou t minus alpha dou square u by dou x square at I comma n, right? This is nothing but our exact partial differential equation. So this is basically satisfied by u. So this is equal to 0, right? This is now satisfied. This is satisfied at every grid point is what we say. So essentially this is equal to 0 because the equation is satisfied. Okay, so this is equal to 0. So our truncation error is now order delta t, and so that is order delta t term, and here it is order delta x square, right? That is what we have. That means we can say that the truncation error for the one-dimensional transient heat conduction equation is, so truncation error is order delta t, that is first order in time, and then order delta x square, that is second order in space. Okay, now from here you might wonder, like, we have done such a long procedure which we could have avoided, because we already know in the first place that if it is a one-sided difference, we know that essentially one-sided differences are first order accurate, right? I mean, although we have not written a one-sided difference in time till now, we know that if I had written instead of this ui plus 1 minus ui divided by delta x, that would have been order delta x accuracy. Similarly, instead of I plus 1 and I wrote in terms of n plus 1 and n, right? I have missed an n here. Okay, then this is going to be order delta t. And then, of course, on the right-hand side, we have this is a central difference scheme for the second derivative, that is r equals 2 and m equals 2. We know that this scheme is actually second order accurate. Then if I put these together, essentially we're going to end up with order delta t from the time derivative and order delta x square from the space derivative. In fact, that is what we ended up with, right? So it might look at first that this is actually not required, because you could guess it from the corresponding discretizations that we have already. Okay, but it is not so. We will see that it is not, although it sounds very straightforward like that, but it is need not necessarily match with what you have given there, or it may be in fact not possible to put in these numbers so easily in the discretization, before we do this kind of analysis. Okay, so what does that mean? That means that the explicit Euler method, when applied to the one-dimensional heat conduction equation, is first order in time and then second order in space. That means if you're going to reduce your delta t by half, then the truncation error that is associated in time is only going to become half. Whereas in space, if you're going to make your delta x 2 delta x by 2, then the truncation error is going to go down by 4 times. Okay, so that is what it means. Okay, this actually is not all of it. This equation also gives us some more information. For example, if you look at the second term that is there, the second set of terms here. That means if I'm going to choose my delta t and delta x such that I want to get rid of these two terms also from my discretization, from my truncation error, then I can actually end up with truncations that are order delta t square and order delta x power 4, right? I can actually make this scheme behave like a higher order accurate scheme if I can choose my delta t and delta x such that this second term actually also disappears, just like the first term has disappeared, right? That means what should I do? That means I should basically make this first quantity equal to the second quantity. That means I should do delta t by 2 utt, delta t by 2 utt equals alpha delta x square by 12, alpha delta x square by 12 u for x. If I can satisfy this condition by appropriately choosing my delta t and delta x, then I can basically make them, both of them equal, and one of them comes with a positive sign, the other one comes with a negative sign, so they get cancelled. Then my leading truncation error would be order delta t square and then order delta x power 4, in which case I'm happy because my scheme, although it is explicit Euler, which is first order in time and second order in space, has become second order in time and then fourth order in space. Okay, so that is kind of nice. So, but then how do you do this? That means I can look at what is UTT. UTT is your dou square u by dou t square, right? We recall our equation is dou u dou t equals alpha dou square u by dou x square. So this is our governing equation. Okay, but then I am now working with dou u u sub dt, that is dou square u by dou t square. I can write this as partial t of partial u by partial t. Okay, but then I can substitute for the dou u dou t from here, which is as alpha dou square u by dou x square. Okay, if that is the case, I can write this. Alpha is a constant, so alpha can be brought out. Similarly, I can also, assuming that the time derivative and the space derivatives commute, right? That means I can do time derivative of the space derivative, or I can do space derivative of the time derivative, right? If I can exchange this thing, then I can write this as alpha times dou square by dou x square of dou u by dou t, right? If the space and time are independent, then I can do that. I can exchange the order of differentiation as dou by dou t of dou square u by dou x square as dou square by dou x square as of dou u by dou t. Okay, if I can do this thing, then what I have is dou square by dou x square. I have dou u dou t again, but dou u dou t from my governing equation is again alpha dou square u by dou x square. If this is the case, what I have is alpha square dou to the power 4 u by dou x power 4, right? That's what we have. That means my dou square u by dou t square came out to be alpha square dou power 4 u by dou x power 4. That means if I'm going to put this back in here, now I did this thing for a purpose because I have time derivatives here and I have space derivatives here, but then by using this transformation, I have converted my double time derivative into actually a fourth derivative in space, which happens to be there on the right hand side as well. So I'm going to write down this equation, delta t by 2 utt equals alpha delta x square by 12 u x. Okay, but then I can now substitute for utt from the above equation. That is delta t by 2 alpha square dou power 4 u by dou x power 4 equals alpha delta x square by 12. This is also dou power 4 u by dou x power 4. Okay, that means now I just need to equate these two guys. One alpha gets cancelled. one alpha gets cancelled. Then what I end up with is delta t times alpha by 2 equals delta x squared by 12. That means delta t equals delta x squared by 6 alpha. So once you have decided on the delta x, that means once you take some domain L and you have put in, let us say, n number of points, that fixes your delta x, right? You take it as L by n or L by n minus 1, depending on how you have counted, whether from 1 to n or 0 to n. So once you have delta x, if you take square of the delta x and divide it by with c times alpha, alpha is the thermal diffusivity, then if you can take your delta t exactly to be equal to that value, then it so happens that the second term, second set of terms, or these two terms also vanish, and then your scheme actually behaves as a second order in time and fourth order in space. Okay, so that can be that is something interesting information that this particular truncation error expression tells us, right? We can selectively choose your delta t such that you can make it higher, you can make it behave like a higher order accurate scheme. But then actually this is not quite nice, because what happens is in practice the value of delta t will come out to be too small to be used. Okay, because too small to be used, because you are already dealing with delta x is small, and then square of that is even smaller, and then you are dividing with 6 alpha and all those things. So as a result, delta t will become prohibitively small or very small. As a result, we won't be able to actually use it in this sense for bigger problems. Okay, for simple one-dimensional problems, we might be able to use it. Okay, now now let us comment on the consistency of explicit Euler method. Okay, so if you see, what we have is our truncation errors are actually of this fashion, that is delta t by 2 utt minus alpha delta x squared by 12 uxx, right? That's what we have. So that means if you look at the truncation error, if I make delta t smaller and smaller, this term will approach 0. Similarly, if I make delta x squared smaller and smaller, this whole term approaches 0. That means we can say that because of the way the truncation error expression contains delta t and delta x, as you make them smaller and smaller, these terms become 0. As a result, this scheme can be said as a consistent scheme. Okay. So as I make my delta x smaller and delta t smaller, we know that the truncation error, which is of the order of delta t by 2 utt minus delta x squared by 12 u x u x x x x and so on, also goes to 0, right? Because delta t and delta x are made to 0. So as a result, explicit Euler method is a consistent method, right? Because then the truncation error goes to 0 as you make the mesh refined. Now, do you expect a method to be inconsistent? You may wonder, like, why will any scheme be inconsistent? Do you think any method can be inconsistent? If it is inconsistent, how would the truncation error might look like? Can anybody guess? Let us say, for example, in the expression for truncation error, instead of getting delta t and delta x squared in the numerators, you may get something like 1 by delta some term or 1 by delta x some term, something like this. If you get something like this, then what this means is that as you make delta t smaller, your truncation is actually increasing. Similarly, delta x smaller, your truncation is actually increasing. Okay, you may not get terms like this, but they may get terms like delta x squared by delta t and so on. In which case, what happens is that as you make delta x small and delta t small, instead of them going to 0, they actually tend towards a constant value, right? So they may tend towards a constant value. As a result, your method will not become consistent, or it will not reach to truncation error of 0. Rather, the truncation error will reach a constant value. Okay, although you refined your mesh and delta t and delta x. Okay, so this can happen many times in any of the simulation software you would use. You will see that sometimes, okay, I have taken a very fine mesh, I have taken a very tiny small delta t, but it appears my solutions are more different from what they're supposed to be. When I worked with a cell size of, let us say, 2 millimeters, I'm getting better result. When I made the mesh size to 0.5 millimeters, my solution is actually worse. How can you explain this phenomena? You might have run into some problem like this. Or you might say, okay, delta t, when I have taken it to be some 10 power minus 3, I'm getting better result. The moment I refine my delta t to 10 power minus 4, my results are actually bad. So this is happening because one of the schemes that you're using is actually inconsistent, right? Either in the truncation error expression, there are the delta t, delta x are not there only in the numerator, or there are expressions where you have some delta x by delta t to the power some coefficients, exponents, something like this, which are basically making your truncation error to reach a constant value instead of decaying to 0. Okay, when you have such inconsistent scheme that is used in the discretization, then this is very much possible. In fact, there are such schemes in the literature which were proposed. Although some of these schemes have good properties, they are inconsistent. So we should not be working with inconsistent schemes, because you would not know why the error is increasing when you are actually making your mesh and the time step smaller and smaller. Okay, so that is about consistency for the explicit Euler method. Okay, any questions so far? Questions or comments?
No, sir, not at this time. We'll review and get back to you, sir.
Okay, fine. All right. So then let's move on to the other method. So other method is the implicit Euler method. Implicit Euler method. Okay, but then it will follow very similar steps. Okay, so I'm not going to do this. You can do this as a later during your free time. You can try to do this during your free time. Okay, do this as a homework or something. It will come out to be very similar. It will also have implicit Euler, will also have order delta t, order delta x square, and you can show that this is also a consistent method. Okay, you can show that. Fine. Now let us look at the third scheme that we have learned, that is basically the Crank-Nicolson method, CN scheme. Okay, so what was the first starting step in working out the truncation error is using the scheme to discretize the governing equation, right? That means we will write this governing equation, which is given as dou u by dou t equals alpha dou square u by dou x square. We're going to write the corresponding Crank-Nicolson discretization of this thing, which we have already written as ui n plus 1 minus ui n divided by delta t equals alpha by 2 ui plus 1 minus 2 ui plus ui minus 1 by delta x square, all at n plus 1 plus ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square, all at n. Now, as you can see, because there are several terms on the right hand side, and unlike the explicit method where everything was in terms of just n, we have now in terms of n and n plus 1. And we also said that the Crank-Nicolson method is discretized about n plus half. Okay, that needs to be kept in mind as well. So because of all these complexities, you can expect that the expression for truncation error, or the expression that we are going to derive for truncation error, is going to be really long. Okay, but nonetheless, we are going to do that so that you can keep track of this thing. So now we never had terms like this. For example, we never had previously ui plus 1 n plus 1. This term was not there. Either we had ui n plus 1 or we had ui plus 1 n, but not ui plus 1 n plus 1. And to add to that, we are not actually expanding. We are not writing the scheme about either n or about n plus 1, we are actually writing this about n plus half. Okay. So as a result, I'm going to expand everything about I and n plus half. So we're going to choose our ith grid point and n plus half as the point about which we're going to expand all these values. Okay. So when I look at the first terms again here, um, so again, we said this is the truncation error. So we say that initially, okay, so I should have written this because this is the final difference equation. So this entire thing is written in terms of capital UI, right? Not in terms of small. We should have written everything in terms of capital UI. But then again, all these are in terms of capital UI and so on. But then we know that the truncation error by definition is equal to the algebraic equation satisfied the exact analysis condition, the amount by which that doesn't satisfy the algebraic set of equations. That is your truncation. So that means I'm going to rewrite this equation in terms of little u. Okay, so ui n plus 1. So it's basically a repetition, but we do that for the sake of understanding. Minus 2 ui minus 1 by delta x square at n plus 1, n plus 1, n plus 1 plus ui plus 1, 2 ui, delta x square, n. Okay, that's what we have. Now, let me expand ui n plus 1 about ui n plus half. Now, ui n plus 1 is away from ui n plus half by delta t by 2, right? So, this is going to be plus delta t by 2 ut. Okay, when I write ut, we know that this is at u and I n plus half. So we will not write this I and n plus half for each of the terms, but we keep at the back of our mind that we remember that all these derivatives, all the things that we are writing here are all at I and n plus half. Okay, and then we should be cautious of what is the time step between ui n plus 1 and n plus half and n plus 1. That is only delta t by 2. So this is going to be delta t by 2 whole square by 2 factorial. That will come out to be delta t square by 8, right? Okay, and then we get utt plus we're going to get delta t by 2 whole cube, that is delta t cube by 2 cube 8 times 3 factorial 6, that is 48 u triple t plus delta t for 4 by 4 factorial, that is 24 times 2 power 4 16. Okay, we may not write this thing. Okay, let us say, let's leave it here. So that's what we have. Okay. So then what about the next term? The next term is uin. So this is going to be uin equals. Now I want to expand uin also about ui n plus half. We always want to expand about only about the same point, either it is uin or uin plus half, because when you either subtract or add, these guys are going to be either get cancelled or they stay. Fine. But then we realize that uin is minus delta t by 2 off from n plus half, right? We have to go back by minus delta t to reach uin from uin plus half. So this is going to be minus delta t by 2 ut. Again, this is I and n plus half, which we will conveniently not write all the time. And then plus delta t square by 8 utt minus delta t cube by 48 u triple t and so on. So that's what I have. That means if I'm going to subtract one equation from the other, because that is what I have on the left hand side, uin plus 1 minus uin by delta t, this is going to be uin plus 1 minus uin equals, okay, let me write divided by delta t also. That is going to be subtract these two, second one from the first one, divided by delta t. So the first term is going to get cancelled because this is uin plus half, uin plus half. Second term is going to get added up. So this is 2 halves, that will become 1. And then you are dividing with delta t. So delta t is gone. So we end up with just ut. And again, the third term will get cancelled because this is plus, this is minus, or this is plus and plus. The fourth term will get added. So you're going to get delta t cube, but then you're dividing by delta t. So it will become delta t square divided by 2 halves will become 148 will become 124, right? 1 by 48 plus 1 by 48 will become 2 by 48, that is 1 by 24, and then you'll have u triple t plus and so on. Okay, that is what I have. So this is the expression for the left hand side. Now everything on here is in terms of at I and n plus half. That's what we have. Okay. That is what we have. Okay. Now we have to deal with what is on the right hand side. Right hand side, we have again um, the similar expression as we had before, but then now things are at n plus 1 or at n, right? So let me start with n plus 1. Okay. We have already written. So what we have is ui plus 1 minus 2 ui plus ui minus 1 divided by, let me bring this 2 inside. So I'll write 2 delta x square and 2 delta x square divided by 2 delta x square. This is equal to, what did we get? We have already, no, not 2 delta x square, just delta x square. Let's leave the 2 outside. Okay, so we have derived this formula before. What was this? This was in the context of explicit Euler. We have done this. Yeah, so we have it here, which is nothing but uxx plus delta x square by 12 u4x, right? That's what we have. But everything is at time level n, right? So these are also at time level n is what we have. U double x plus delta x square by 12 u4x is what we have. Okay. So let me write that here. So this is going to be u double x plus delta x square by 12 u 4x, but then everything is, let us say, if you are writing at n plus 1, n plus 1, n plus 1, this is also at n plus 1 and n plus 1. Okay. But then to be able to put into one equation, we want everything to be at n plus half instead of at n plus 1. So that means I can simply write that, let us say, a short form, this is delta x square. Okay, this is delta x square operating on ui at n plus 1. If I were to write this thing, so instead of rewriting this, I'm writing this expression. This is nothing but uxx n plus 1 plus delta x square by 12 u 4x n plus 1. Okay, but then I want to now expand this guy, each of these terms about n plus half. That means, let me start with the first term here. So this is going to be uxx n plus half. Okay, I'm expanding the first term about n plus half. So again, we know that n plus 1 is plus delta t by 2 away from n plus half. So this is plus delta t by 2. Then we need to take one time derivative of this function. That means it's going to be, instead of xx, you're going to get txx plus you will get delta t square by delta t by 2 whole square by 2 factorial. That's going to be delta t square by 8. And then you get 2 time derivatives on top of the existing 2 spatial derivatives plus delta t cube by 48. That is 6 times this thing. And then you'll get u 3 time derivatives and xx and so on, right? This is all the expansion for the first term, right? This is all the expansion for the first term. Now let us look at the second term. Okay, the second term is basically plus you have delta x square by 12. Okay, then again this is at n plus 1. I'm going to expand about n plus half. So this is going to be u 4x at n plus half plus delta t by 2 u t and then 4x at n plus half and delta t square by 8 u t t 4x at n plus half and so on. Okay, that's what we're going to get. Okay, so this is for expanding about n plus half, right? That's what I have. Now let me also write, so what is the next term? Next term is exactly the same term evaluated at n, right? That means I'm going to write the other term as delta x square ui at n, right? Just like I have at ui n plus 1. So this is going to be the uxx at n plus, just like here, this is going to be delta x square by 12 u 4x at n. Again, we want to expand these two guys about n minus n plus half. And we realize that to get to n from n plus 1, we need to go in the minus delta t by 2 step, right? That means the expression is going to be exactly similar to this one, right? Except that the odd derivatives will have minuses and the other derivatives will have plus. So this is going to be uxx n plus half minus delta t by 2 utx plus delta t square by 8 u ttxx Then you'll have minus delta t cubed by 48 u triple t xx plus and so on. Okay. And then you have plus delta x square by 12 times u 4x and plus half minus delta t by 2 u t 4x and plus half plus delta t square by 8. You'll get u tt 4x and plus half and so on, right? That's what we have. Okay. So now what is there on the right hand side? On the right hand side, what we have is summation of these two terms, right? We have delta x square uin plus 1, delta x square uin, and then multiplied with alpha by 2. That's what we have on the right hand side. So left hand side we have already worked out, that is this quantity. Okay, that means on the right hand side we have a summation of this quantity plus this quantity, right? That is delta x square ui n plus 1 plus delta x square uin. You can clearly see that when we want to add these two guys, the uxx n plus half will get added 2 times, right? So we're going to get uxx n plus half. That's going to be 2 times. Then the time derivative plus delta t by 2 and minus delta t will get cancelled. And then you end up with delta t squared by 8 and delta t squared by 8. That will become plus delta t square 2 times delta t squared by 8 u tt xx and so on. And then plus you will get delta x square by 12, that is for the second terms. You're going to get this u4x values which will get added. So uxxxx at n plus half, this is going to be 2 times. Then the second term in terms of plus delta t by 2 minus delta t by 2 will get cancelled. This will become again 2 times and so on, right? Essentially this will become again 2 times delta t squared by 8 u tt 4x and so on. Okay, that's what we have. Okay, so okay, so then this is the term we have. Then if you go back, you have essentially you have multiplication with alpha by 2. I have just summed these two. That means I have to also multiply with alpha by 2. So alpha by 2 times delta x square ui n plus 1 plus delta x square uin is going to be alpha times this 2 will get cancelled with this 2. That's going to give you simply uxx n plus half. Okay, I don't even have to write n plus half all the time. And then plus the 2 will get cancelled. You'll get delta t square by 8 uttxx. And then again plus you will get delta x square by 12. 2 gets cancelled and then you have uxxx. And then you have plus delta t square by 8 times utt x, 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 and so on. Okay, and then of course this is also multiplied with delta x square, right? Delta x square is multiplying the first term as well as the second term. Okay, so I'll just take a minute to finish up this thing. So when I put everything together, what I get is essentially, if I go back, so this is for the first term, right? ut plus delta t square by 2 and so on. And then this is for the second term and that is on the right hand side. So I can write for the total truncation error ut plus delta t square by 24 u triple t. So the truncation error is going to be ut plus delta t square by 24, delta t square by 24 u triple t, and then minus alpha times uxx. I'm not writing the superscripts. And then you have minus alpha delta t square by 8 u double t xx minus alpha delta x square by 12 u plus order delta x square delta t square, right? That's what we have. This is the truncation error, right? This is the truncation error. Now you see that the first term ut, that is dou u by dou t, and then minus alpha dou square u by dou x square. Order delta t square term from here, and then order delta x square term from here. And then of course you have higher order terms. That means the truncation error is second order in time and second order in space for the Crank-Nicholson scheme. So this is a very good thing because by just discretizing about n plus half, we are able to get second order in time and second order in space, unlike the explicit Euler and implicit Euler, which are only order delta t, order delta x square, right? This is what our explicit Euler and implicit Euler were. Okay, so that's why Crank-Nicholson scheme is preferred over the explicit Euler, implicit Euler, because with we will be able to get second order accuracy in both space and time. Okay, so that's what this is about. Okay, I'm going to stop here. We are off our time limits by 5 minutes. I'm going to stop here. If you have any questions, you can ask me. Otherwise, we're going to meet on Monday is a holiday on account of Deepavali. We're going to meet on Tuesday, 21st. Okay,
Sir,
for our lecture.
Tuesday class is available, sir, because we are having leave holiday.
You have a leave on Tuesday, is it? Yeah, Tuesday we have, I mean, for us, Monday is holiday.
Okay.
Yeah, Tuesday we'll have a lecture.
Okay.
Will all of you be able to join, or should we take it on some other day or time?
So is it better, sir? We can do it on Thursday or something else, sir.
We'll move it to another day or something like that.
Yes.
Based on your availability, we can have a conversation.
Okay. Then what we will do is that then let's not meet on Monday and Tuesday both. Okay. Let's meet on Wednesday, 22nd.
Yes, sir. Sure, sir.
That's okay.
Okay, Wednesday, 22nd. I'll make up for this lecture depending on how it goes. Okay.
Okay, sir.
We will see whether to take an extra lecture, or maybe I'll post a. I think we'll make up an extra lecture sometime, either on Thursday or something like that.
Sir, one more a small obligation from our side, sir.
Yeah.
The second assignment submission date on 22nd. Is it possible to?
Oh, it's 22nd. Okay, we'll move it to. It's on 22nd. Right? Shall we move it to 24th or something?
Yeah, 25th is okay for us, sir. 23rd we will come. Yeah.
Sure. I'll ask the code office to extend it. So
yes,
I'll also inform that we are not meeting both on Monday and Tuesday. We'll meet directly on Wednesday. Okay.
Yes, sir. Yes, sir.
Yeah, on 22nd we'll meet. Okay.
Thank you, sir. Thank you very much, sir.
Thank you, guys.
Thank you, sir. Okay.
Yeah.
Happy Diwali, sir.
Thank you. Happy Deepavali to you, all of you as well. I'll extend the assignment deadline to 25th. Fine.
Yes, sir. Yes, sir.
All right. If you have any questions, feel free to ask me or write to me or something like that. Okay. We have TAs and I'm there. Fine.
Sure. Sir.
We'll
right,
take
sir.
care. All right. Yeah.
Thank you.
Thank you.
sir.
Bye.
Thank you, sir.
Thank you so much.
Thank you, sir. Yeah, happy Diwali.
Thank you. Happy Deepavali to all of you as well.